Welcome student to the course of physics of linear and nonlinear optical waveguides. Today we have lecture number 14, and in this lecture number 40 we will going to learn about the working principle of WDM coupler. So, today's topic we will going to learn WDM coupler, so which is wavelength division multiplexer. Or WDM. So, what is the WDM coupler? So, let me draw that. So, this is the standard coupler system we are drawing every day. So, here what happened that if I launch two wavelength, say one wavelength is lambda 1 and another wavelength is lambda 2. So, I launch two wavelength lambda 1 and lambda 2. In the output what I want that two wavelength should separate. So, lambda 1 wavelength will come to this branch and the wavelength lambda 2 should be here in this branch. That we can do also using the principle of coupler. So, we should write the power, what is the expression of the power. This is the expression of the power transfer from one branch to another branch. So, let me write it once again. So, there is a square associated with that. This is the expression with the condition when delta beta tilde is not equal to 0. Well, when I am launching a light having two different wavelengths, say lambda 1 and lambda 2, then I must say the coupling constant kappa, whatever the kappa so far we are using, should be a function of lambda. So, that we need to take account now. So, coupling coefficient, so that means coupling coefficient is now in general a function of wavelength. It is a function of in general function of wavelength. So, that means for lambda 1 and lambda 2 these values are different. Now, let us consider to make life simple, this is equal to 0, delta beta tilde is equal to 0. If I put delta beta equal to 0, then P1 the expression will be simpler. So, P1 divided by P0 should be equal to cos a square of kappa z, and P2 divided by P0, which is a function of z, is equal to sine square of kappa z. Now, I mentioned that kappa is a function of lambda. So, for lambda 1, kappa should be equal to kappa 1, and for lambda 2, kappa should be equal to kappa 2. So, better to write in this way, kappa as a function of lambda 1 at lambda 1 is this, kappa at lambda 2 is this. So, I can have two different kappa because now my wavelength is different in the system, it is lambda 1 and lambda 2, two wavelengths are there. So, my kappas are different. So, now if the kappas are different, so I can, these conditions are different for different lambdas. For example, P1 will be equal to P0 when kappa 1 L is equal to m pi. So, for wavelength lambda 1, I can have P1 equal to P0, and if I use the kappa for wavelength lambda 1, then this condition at m pi, so the power will totally convert it from branch 1. So, the power will come to branch 1. So, this is for wavelength lambda 1. So, this is the value at which in the branch 1 I have entire power. So, this is the coupler and I have lambda 1 here. So, there will be a transfer, but in the output I can have my lambda 1 here, because this is branch 1 and this is branch 2. However, when P2 equal to P0, is this condition one can have when kappa 2 L is equal to m plus half pi, and this is for wavelength lambda 2. So, that means for lambda 2 what happened? This is the waveguide we have, this is the waveguide we have. I launch a lambda 2 here in waveguide 1, but this lambda 2 will come here. This is 1, this is 2. So, I want the lambda 2 in branch 2. If I want the lambda 2 at branch 2, this condition has to follow. Well, with this idea, we can find out the length at which both the conditions satisfy simultaneously. What is the condition? So, let me write it here. So, we have for lambda 1 wavelength P2 lambda 1 at some distance L is equal to P0 sin kappa 1 L to be 0. That means, I do not want any kind of wavelength at output at second P2 means at second branch, and for lambda 2 wavelength I can have P2. So, this is lambda 1, this is lambda 2 L equal to P0 sin square kappa 2 L equal to P0. So, in the second branch, so what I am trying to do is this. So, this is the second branch. I want to have my, so this is lambda 1 say, and this is lambda 2. So, in this branch I only have lambda 2, but at the same time I do not want lambda 1. So, lambda 1 if I write, so I do not want this. So, these things should I cross. So, I do not want. So, I have both the conditions here, the same condition for lambda 1 and lambda 2. I put the equation which is same. In one case I have lambda 1, in one case I have lambda 2, and in other case the equation is same, but I do not have lambda 1. This equation is for lambda 1 and this equation is for lambda 2. So, this condition, if I look carefully, satisfied when kappa 1, that length L is equal to m pi, say m equal to 1, 2, 3, 4, so on, and simultaneously kappa 2 for the same length, it has to be m minus half pi. So, from these two expressions one can extract what is the value of the L. So, L I can extract, which is pi divided, if I just make this minus this, so it should be simply, so okay, let me do that clearly. So, I can have kappa 1 minus kappa 2 L is equal to simply pi by 2. So, my L, the critical length at which these two wavelengths will be separated out, should be 2 of kappa 1 minus kappa 2. So, this is, so this is the critical coupler length corresponds to the fact that lambda 1 will exit from the same fiber where as lambda 2 will exit from other fiber. Other fiber means waveguide 2. Same fiber means waveguide 1. So, I already draw that if this is waveguide 1 and if it is waveguide 2. So, lambda 1 will going to come here and lambda 2 will be here, where there is no lambda 1 here in waveguide 2. So, I just put this condition, and after putting this condition I can have the length L equal to pi divided by 2 multiplied by kappa 1 by kappa 2. This is the critical length at which this condition, this thing may happen. So, we quickly write down the example. So, one example. So, consider a coupler with identical fiber such that say N1 for lambda 1 is equal to 1.4525 and N2 which is for lambda 2 is equal to 1.45. So, the refractive index of lambda 1 is this and refractive index for the lambda 2 is this, where lambda 1 is say 1.55 micrometer, lambda 2 is say 1.3 micrometer, and the coupling coefficient kappa 1 is equal to 6.496 centimeter inverse, and kappa 2, this is for lambda 1 and this is for lambda 2, 4.872, this is point centimeter inverse. So, lambda 1 and lambda 2 is given for these two lambda kappa 1 and kappa 2 is given for these two lambda 1 and lambda 2, and I can calculate readily, I can calculate what is my critical length at which this separation of the wavelength happens, and that we already calculated. It is pi divided by 2 kappa 1 minus kappa 2. kappa 1 and kappa 2 value is given. So, I can calculate that. So, L is equal to pi divided by 2 of kappa 1 minus kappa 2, which is equal to 9.67 nanometer. If you calculate that, it should come like this. Well, once we know the value of L, then I can find out one thing. So, for this interaction length, what happened? So, for this interaction length, we can have kappa 1 L is coming out to be very close to 2 pi if we calculate, because we know L, we know kappa 1. So, kappa 1 and L should be very close to 2 pi, and kappa 2 L will be around 3 by 2 pi. If you calculate, you will find this. Now, the general coupling, note in general, the coupling length is given by LC is equal to say pi by 2 kappa. This is the coupling length we know. So, for lambda 1, you can see for lambda 1 what happened, whatever the length is there divided by coupling length. So, this is the length, L is the length of the coupler, and I want to find out how many coupling length are there for lambda 1. I can calculate that. So, L I know this is 2 pi divided by kappa 1 multiplied by 2 kappa 1 divided by pi. So, this is the value I know, pi divided by 2 kappa LC, and L I can calculate from this calculation, which is 2 pi divided by kappa 1. So, I just put this value 2 pi divided by kappa 1 multiplied by 1 by LC. 1 by LC is 2 kappa 1, it should be kappa 1. So, this value is equal to 4. So, the total coupling length, total coupler length is equivalent to the 4 coupling length for lambda 1. So, what about for lambda 2? For lambda 2, this value L divided by LC, which is equal to 3 pi divided by 2 kappa 2 multiplied by 2 of kappa 2 divided by pi, which comes out to be 3. So, that means if I draw this stuff, it should be something like that. So, this is the total coupling length, and in total coupling length I have the total coupler length is L, and the coupling length LC is 4 times coupling length LC is my total length. So, this is one coupling length, this is another coupling length, this is another coupling length, and this is another coupling length. So, I have this total length of the coupler, which is L. So, this is 1, and this length is my LC. This is another length 2, this is another length 3, and this is another length 4. So, you can see this is channel 1 and this is channel 2. So, output, this is the output of channel 1. This is the output of channel 1. What about, and for lambda 1 as well, because this is for lambda 1. So, this is for lambda 1. What about lambda 2? The same thing, if I draw the same scale, and I do make it in same scale. So, my total length L is same. So, let us first draw my total length. So, this is the length at which, this is the length of the coupler for which I am having is. So, now if I draw for lambda 2 the ratio of total length L and LC, we already figured out for these two. Here we have the curve like this. This is one length, this is second length, and this is third length. So, this length is 1, this length is 2, and this length is 3. What is this length? This length is the coupling length for lambda 2. These two are not same, and this is the output of channel channel 2. So, that means I now have, this is the structure, this is the structure, this length is L that I calculate, and what is L? L is equal to pi divided by 2 kappa 1 minus kappa 2, that I find. And what happened? The two wavelengths are launched here. For lambda 1 we have 4, for lambda 1 we have these 4 coupling length that we are going to cover in this length. So, 4 times the energy will come. So, initially it was here, then it should come here, the second point, then initially it was here, then come here, and then again come back to here, again come back to here, and finally I can have this. So, this is 1, this is 2, this is 3, and this is 4th length. On the other hand, what happened for other wavelength? Initially it was here, so I draw these things together, then it comes to here at some point, then it come to here some point, and finally it goes back here. So, this is 1, this is 2, and this is 3. So, finally at the output I have the wavelength here lambda 1 and I have the wavelength here lambda 2 in another branch. So, this is 1 and this is 2 if I write in terms of branches. So, I hope you understand the working principle of the WDM. So, this is basically the working principle. I try to derive everything from the first principle, so that you can understand what is going on, the physics behind that. So, I will conclude here this discussion. So, in the next day we will start a brand new topic called fiber bracketting, which is a very important topic, and lot of research is going on in recent times on fiber bracketting. Many applications are there, but in our course we are going to study the physics behind that, the working principle of what is going on in the fiber in terms of fiber bracketings. So, with that note I would like to conclude. Thank you for your attention. So, see you in the next class.